important fundamental research is being carried out without very much fanfare in what is known as the Low Temperature and Solid State Physics Laboratory of the National Research Council. With me in one of the offices of the laboratory to discuss this work and its possible application in the future is Dr. D.K.C. MacDonald, head of the laboratory. Dr. MacDonald, just what does the Low Temperature Laboratory do?
Well, nominally, as you know, we are called the Low Temperature and Solid State Physics group here. Sometimes, I'm afraid, I feel I want to point out to people that it might be better if we were called the High Temperature and Liquid State Laboratory, because we don't necessarily confine ourselves just to worrying about low temperatures. To a certain extent, the whole of physics fascinates us. But specifically, we are concerned with the physics of materials, particularly metals, as a matter of fact, at extremely low temperatures, the fundamental behavior of them.
Is this better for you? Why can you do your research at low temperatures rather than high temperatures?
Well, there's an analogy I sometimes like to give. I'm afraid I sort of overwork it a bit. But if you look right out my window just now, Mr. Bird, you can see there trees waving in what's almost a small gale out there just now. Now, I doubt whether you'd be able to tell me exactly what kind of leaves there were on those trees, because they're moving about so rapidly. And even if I gave you a telescope to look through, again, you might find it difficult to pick out the details because the leaves are moving so rapidly. And it's something like the same with the atoms in a body, a piece of copper, a piece of other kind of material, crystal, diamond, anything like that. Even at room temperature, where bodies like this table in front of you and the telephone there and so on, they seem to be completely solid, rigid things. The individual atoms are moving about pretty rapidly all the time, something like the leaves on the trees there, and it's not too easy to determine the fine details of their behavior, of structure and so on. But if you go to extremely low temperatures, you can quench this vibration due to heat in somewhat the same way that if we went out there and forcibly held one of the branches of a tree steady, we could study the details on the leaves in more detail.
What type of temperatures do you reduce metals to?
Well, it's extremely low. Again, one might take perhaps a rather overworked analogy, but if you were listening to, I was going to say tabloid, but it's called 701 these days, tonight, and you heard Percy Saltzman say that it was going to be about 450 below, which presumably would give one rather a shock, then that's the sort of temperatures that we're working at. Temperatures at which even gases like hydrogen, which one thinks of as an extremely light volatile gas, has become a liquid, nay, even a solid in fact, and helium even becomes a liquid. Expressed in centigrade degrees, one is talking about temperatures about minus 270 degrees centigrade, and in the Fahrenheit scale around 450, that sort of thing, 450, 460 degrees below zero.
I've heard that you can't reduce anything to absolute zero. Why is this?
Well, I should have, suppose, have said there that there is in fact an absolute zero of temperature, not to be confused with the meteorologist's zero, which is, in other words, one is talking there, as a matter of fact, about 0 degrees Fahrenheit. The absolute zero of temperature lies at about minus 273 degrees centigrade. Lord Kelvin first showed us that there must be a lower limit. I think you can understand it this way. Give you perhaps an example. If you were a housewife, if you are a housewife with small children, you may easily come into the house sometime and you look at the rooms and you have 3 small boys rushing about, and the usual cry is to sort of find yourself saying, there seems to be no limit to the amount of disorder that these children can kick up in this house. Well, in somewhat the same way, when atoms are vibrating or moving around, this is disorder and it represents heat. And so one might reasonably guess, and as far as we know it's true, there is no upper limit to temperature. You can always make more and more disorder, and in fact, man does it pretty successfully when he makes an atomic bomb or a hydrogen bomb. He makes vast amounts of heat. And as I say, as far as we know, you can go on and on doing this in principle. On the other hand, even a housewife is sometimes able to say, now look, this house is in complete order. You children are not to go near it because I've really tidied it perfectly well. And somewhat the same way again, one can visualize a state where the atoms and molecules are in a complete state of perfect order. And you can't imagine anything more order than that. Let's put it that way. Well, that is the absolute zero of temperature. So there is this lower limit. Now, I think you were asking specifically that you can't reach this. Is that the state? Well, again, this is perhaps, it's not easy to answer why exactly you can't reach it, except that each time what you can always do is to improve the degree of order. Every time you improve the order, let us say by a certain factor, you can see more and more the details of energy structure and of bodies. But roughly speaking, each time you've done it a bit, you can go a little bit further, but there is no possibility really of reaching the absolute zero of temperature. This is a state, so to speak, put it this way, it could only be reached by being at that state already, we believe, and one can never actually reach it. But that doesn't mean to say you can't go as far along the road, probably as you please.
What are some of the projects which are underway here which might have a application in our life later on?
Well, I think one thing I would like to say here is that while there may well be applications, and one can never tell in pure research, as it's called, when something is later going to have an application. For example, in the last century, mathematicians, pure mathematicians, developed what was called the tensor calculus as a pure piece of theoretical work, and it turned out later that this was just what Albert Einstein wanted, so to speak, for investigating the general theory of relativity. But that's not why the mathematicians did it. They couldn't see ahead. Now, I really can neither tell, nor, frankly, am I personally terribly interested in whether any of the work that we are doing will actually produce practical results. In fact, if one did, one wouldn't probably be doing the best pure research, because it would tend to limit what one was working at. One would tend to be sidetracked.
You become commercial rather than science.
Well, I think perhaps that's almost a bad word, isn't it, commercial? What I really am getting at, though, is that one would tend to be deviated from what might ultimately turn out to be much more fundamental, well, I was going to use discoveries, that's rather a flattering word. One of the things I'm particularly interested in myself is the fundamental theory and behavior of thermoelectricity. That's the interrelationship, if you like, of heat and electricity, particularly in metals, I'm particularly concerned with. But already today, this is finding wide applications. It can be used for refrigeration. You can pass an electric current through a pair of metals, a junction of metals, and you can cool one junction and heat another one very readily. And as a matter of fact, I believe the Russians have done quite a lot of actual practical application of this, where they're out in rather isolated parts, where they want either to convert heat into electricity or to be able to produce cooling effects. Mind you, the basic effect has been known for a long, long time. Peltier was I think I'm right, a French watchmaker, and discovered this effect, somewhere around 1830, I think, originally.
I see. I understand that your group is interested in other things than low temperature and solid state physics, that as a group you're interested in many things which are related to this. Could you explain that a bit?
Let me mind you first, I should say there that, of course, people like Dr. Basinski in the group, who's tremendously interested in the fundamental mechanical properties of metals, the strength of metals. Dr. Dugdale does high-pressure work. He uses very high pressures to push the atoms together and achieve order in that way. Dr. Pearson's extremely interested in semiconductors and so on. There's a whole range. But even apart from that, I think a number of us find ourselves interested in, I suppose you might even say, the problems of man. This is I suppose you'd say almost an extracurricular activity, but we have organized in the past 2 or 3 years a number of small symposia on what we call self-regulation in living systems, where we've been able to bring together in a very modest way for a day or so on each occasion neurologists, physicists, chemists, physiologists, philosophers, to discuss in that case various problems which might be of direct interest to all of us. In other words, to try and bring together, I suppose you would say, different disciplines to be able to talk together with one another.
I understand you have written a book in connection with your work, Dr. MacDonald.
It's called Near Zero. How long did you work on this book?
Well, it's a very modest book again that's just come out, but naturally quite proud of it to see it done at last. It's a little book that's meant really for, primarily I think for high school children. It's fostered really by the National Science Foundation, I think in America, who are concerned with the problem of science education in the United States particularly. And the book itself, I suppose the actual writing of it took on and off about a year or so, but it's a thing I've had in mind for quite a long time. I do enjoy very much trying to get over, shall we say, some basic ideas in physics, in particular, I suppose, low-temperature physics, to, well, there's this word layman. I always think that sounds patronizing, but to children, laymen. In fact, children often make the finest audience when one is giving lectures and so on. They're the most enthusiastic audience often. And it's quite a challenge to try and get over some of these ideas, if possible, in not too technical language. And there's incidentally only one equation, I think, in the whole book, which might be a comfort to some people.
Will the book be on sale in Canada?
Oh, I hope so. I believe so, yes.
Thank you, Dr. MacDonald.